In the system section, we should define the lattice type. A crystal structure is identified by two things. First, Bravais lattice, and second, atomic bases. Bravais lattice is an array of unit cells with arrangement and orientation that look exactly the same from any of the unit cells. Bravais lattice defines the shape of unit cell. For example, in this figure, the unit cell is square. Thus, Bravais lattice defines the shape of the unit cell and how it repeats. The Bravais lattice is specified by primitive lattice vectors. I mean A1, A2, and A3. Atomic basis defines how many atoms are in the unit cell and how they are arranged. For example, in this figure, the basis is 3 because we can see 3 atoms in each unit cell. In the case of graphene, the basis is 2 because we can see 2 atoms in each parallelogram-like unit cell. The Bravais lattice are divided into 7 crystal classes. Indeed, in this table, we can see 14 different lattices that are gathered in 7 crystal classes. For example, you can see cubic lattice. It contains 3 sub-lattices, I mean simple cubic, volume-centered cubic, and face-centered cubic named FCC. We can see that the primitive lattice vectors have the same magnitude, I mean A1 equals A2 equals A3, and the angles between these vectors are 19 degrees. Another example is orthorhombic lattice. Orthorhombic lattice is similar to cubic lattice, but lattice vector magnitudes are different, but the angles between them remains 19. Another example is monoclinic lattice. The lattice vector magnitudes are different. The angle between A1 and A2 is not 19 degrees, but the remaining angles are 19. Another example is hexagonal lattice. In hexagonal lattice, A1 and A2 have the same magnitude but differ with A3. The angle between A1 and A2 is 120 degrees and the remaining angles are 19 degrees. In the quantum spatial input file, iBrave defines the crystal type. iBrave means Bravais lattice index. For example, iBrave equals 1 defines simple cubic, iBrave equals 2 defines face-centered cubic, iBrave equals 4 defines hexagonal lattice, iBrave equals 12 defines monoclinic lattice. We should know the crystal structure of each material. For example, silicon has an FCC lattice and graphene has a hexagonal lattice. In the case of graphene, we can define hexagonal lattice or monoclinic lattice. Each lattice has 3 vectors you can see, V1, V2, and V3. As we can see in this relation, we should define A, B, C, and gamma. Gamma is cosine between A and B. From the graphene lattice, we know that A equals B equals 2.45 angstrom. You can see the graphene lattice and the primitive lattice vectors and we can see that the angle between V1 and V2 is 120 degrees. We specify C to be 8 times more than A and B, for example, 20 angstrom. It's due to ignoring the effects of graphene layers on each layer because in this case we want to analyze only the monolayer of graphene. We should write these parameters in system sections A, B, C cosine between A and B. NAT means number of atoms in unit cell. We can see only 2 atoms in each cell, therefore we set it to be 2. While graphene lattice only has one type atoms, that is carbon, thus n-type equals 1. ECOT WFC and ECOT rho are two important parameters described in the next lectures separately.